So what I'm going to do is I'm going to use the time that we have as effectively as possible, but I'm really sorry. I have to cut class a little bit early today. I apologize for that, and I will adjust our schedule and everything like that um, accordingly. I don't want you to think that, oh, great, he's going to, just cram everything in and we're going to go from there. I'm not going to do that. I apologize, though. I know that that is disruptive to everyone else, and so. But anyway, with that in mind, I'm going to go ahead and we are working on enzymes, and we're talking about enzymes. What I am opening right now is week 6, day 2 slide deck entitled Enzymes. So thank you. Um, I am recording, and this is the slide that I'm on. I believe it's number 38 in the slide deck. And this is all about how do we evaluate enzymes. Yesterday, what we talked about is what an enzyme does. And we talked about the different methods and reactions that they catalyzed. We talked about concentrations. We really went into enzymes that have multiple substrates. Now we're going to be getting into how do we study an enzyme and like what is the kind of timeline in which we study an enzyme. Um, so how do we evaluate enzymes? This graph right here is the best to kind of assess and illustrate that. So what we always look at is concentrations, and we look at the lifetime of the reaction. Now, I pointed this out at the tail end of class on Tuesday. We look at substrate concentration, our product concentration, because what we want is we want a chemical reaction to take place. Our substrate or substrates, as it might be, are converted to a product or products. So we'll use this concentration of S and concentration of P. Now, what's also present in an enzyme catalyzed reaction is the free enzyme concentration. And that is represented by E. And then we also are interested in concerned with ES, which is our enzyme substrate complex. So these are all the kind of things that change and all of the things that we monitor. Now, our substrate, our reactants concentration is going to be the absolute highest. Um, it's absolute highest at the beginning of a chemical reaction, or at basically at time point, which I'm going to label it 0. Our product concentration is lowest. In theory, before a reaction's taken place, well, no product is present. We call that what is known as the pre-steady state. Okay, so kind of before the action is going. Now, what we're interested in is we don't want to look at things at time point 0, and we also don't want to look at things like 100 minutes after the reaction's begun, because when we're on the right-hand side over here, what we're looking at that is really more at equilibrium and brium. And when a reaction has reached equilibrium, well, then the rate of product and reactant formation and decomposition, well, those are going to be kind of equal to one another. Those concentrations aren't going to be the same, but the rate of consumption of your substrate is equal to that of the decomposition of your products. What we're interested in is this kind of sweet spot, the sweet spot known as steady state. So if you ever hear the term steady state kinetics, this is that range that we're talking about. And now I don't want you to think like, oh, is this 10 seconds after the reaction's begun? Is it 20? What is it? I don't want you to be focused in on that, but instead think about a reaction as basically being in kind of three different parts or three different segments of time. Pre-steady state, steady state, and then achieving or reaching equilibrium. We're most interested in whenever you study a reaction, you're most interested in the steady state. Now, whenever we're thinking about an enzyme and an enzyme catalyzed reaction and the substrate and the products, I want you to look at these three different models. Here, what we have is our substrate represented by this kind of singular dot there, and then our enzyme as these kind of, our enzyme looking like a little Pac-Man type of figure. This is where we have a low substrate concentration. And then on the far right-hand side, where we have a high substrate concentration. Now, one thing that has not changed there, and this really illustrates how we study enzymes, is we never changed our enzyme concentration. So whenever you're studying an enzyme, you will do a series of trials, and you will do one reaction where you have a low substrate concentration, and then gradually you'll double it, you'll triple it, quadruple it, and you will increase that substrate concentration until you reach kind of a abstractly high substrate concentration. Throughout all of the different trials, one thing that you do not change is your enzyme concentration. Um, okay, so whenever you're studying an enzyme, you'll vary substrate concentration, but you'll basically never vary your enzyme concentration. Now, what that is ultimately going to be, or what that is ultimately going to look like, is plotted on a graph that looks like this. So here, our y-axis is represented as v sub 0. This is our initial velocity. And then our x-axis is represented by our substrate concentration, which is represented, or is that substrate concentration. So our substrate concentration will start out at 0, and it will go on into infinity, or I'll just call it high. And along the way, what you will do as a scientist and as a biochemist is you'll have your substrate concentration be something like 1 millimolar. Then you'll go to 2 millimolar, 3 millimolar, and so on. That substrate concentration for all of your different trials, T1, T2, T3. These different trials is your substrate concentration will be creeping up. That will go up over and over and over again until you reach a point that when you look at your initial velocity, you're going to see that it doesn't change. Now, if you see that your initial velocity, so you could kind of think about this as initial velocity, I'll call it your reaction rate. Let's say you're going through a series of trials and you get the following data: substrate concentration and velocity. Trial 1, you have a substrate concentration of 2, 4, 6, T4, T5. Let's go to 12 and 24. Now, in terms of your initial velocity, you're monitoring product formation versus time. So your velocity or your rate is how much of my product is being generated in a second. So could anyone give me an idea or guess of what units you might use for velocity or for your rate? Molarity per second, moles per second. Awesome. These are great answers. Great job. So let's go with molarity per second. Okay. Let's say in trial number 1, where we use a substrate concentration of 2, and just for the sake of simplicity, I'll call it micromolar. And those units aren't going to change. So 2, and we get 1. And then in trial 2, we've doubled our substrate concentration and we get a velocity of 2 molarity per second. And now from trial 1 to trial 3, we've tripled our substrate concentration and we see our velocity go up as well, which we kind of would expect, but it goes up to 2.5 molarity per second. Okay. Now the change between trials 1 and trials 3, or trials 1 and 2, and then 2 and 3. What do you see between trials 2 and trials 3 in terms of how much your reaction rate goes up? And that's kind of a clunkily worded question, but let me switch it. Does the change in velocity between 1 and 2, is it the same as the change in velocity between 2 and 3? Yes or no? No, it's not. Between 1 and 2, we see our velocity double. Between 2 and 3, it doesn't double. It goes up, basically half as much. So that's a great question. These are just kind of arbitrarily, I'm just putting these numbers in for a model that we're putting together. Does that make sense? These are just like hypothetical numbers. Okay. So let's say hypothetically in trial number 4, which if we look at our substrate concentration, that's 6 times what our initial trial showed. Let's say that in trial number 4, our initial velocity, we monitor it and it comes back to 2.7. No, I'm going to be more conservative than that. I'm going to say 2.55 molarity per second. Okay. Then for trial number 5, we see our velocity go up to 2.56 molarity per second. Trial number 6. Let me ask you, do you think it's really worth doing a trial number 6 with a substrate concentration of 48? Or, I mean, heck, it doesn't really matter the number there. My question is, do you think it's really worth it doing this 6th trial? No. And we can do it just for kind of the purposes of, heck, let's look at the numbers. And let's say it pops up to, let's go with a trial 6 of 36. Do you think that you could guess approximately what the velocity would be based on what you've seen so far? If I told you that it was 2.55, would that make you go, oh my gosh, that's insane? It drops down a little bit, but chances are you're going to see that number and you're going to say, oh, okay. We saw it go up and then it kind of plateaus. So if I were to illustrate this and plot these numbers, I'm going to ask the color and disregard our x-axis is just our substrate concentrations. I'm going to plot this with 2 different colors and you tell me which one's the best or or 3 different colors. And you tell me which one is the most accurate representation of what you are kind of expecting from this data. So there's one color. I can go with green. And then I'm also going to go with blue. Tell me, green, red, or I guess it's like a navy. Yeah, I would go with red because red shows that our substrate concentration causes our velocity to go up. But then at some point, like right around here, the more substrate that we add, the less of an impact it has on our velocity. So the velocity here, or basically the velocity here to here, it's not changing a whole lot. So this range right here, that velocity is barely changing. Can you give me a 1 if you understand that and a 7 if you think, I don't get why it's red? Okay, cool. So this is a pretty standard look at a enzyme catalyzed reaction and the representation of the data for that. Now, I'm going to change slides and looking at this right here, thinking about an oxygen binding curve. Does that look at all like an oxygen binding curve for M myoglobin or H hemoglobin? It might take a second to kind of dig back and, yeah, myoglobin. Yeah, this looks a lot like the oxygen binding curve for myoglobin. Now, if I were to kind of project onto this some of the important parameters for an oxygen binding curve, we've got our y-axis, which shows us that's our saturation point. And then we've got this right here, this halfway point. What is the halfway point on an oxygen binding curve? What is that called? P50. Okay. Now, we're talking about an enzyme here as opposed to an oxygen binding curve. So it's not a P50, but this is an equally as important point. Now, why I'm showing you this is because I want you to understand that the connection between an oxygen binding curve and an enzyme catalyzed reaction activity curve, they're like they're BFFs. They are so interconnected and similar to one another. I want you to kind of acknowledge and appreciate that. Now, we do use different terms. For example, that point on an enzyme activity curve is known as a Km, not a P50. And then this point right here is if you're driving your car and you put the gas pedal all the way down, and at some point the speedometer kind of like stops. What's that also known as? I think it was also a TV show on the BBC. Top speed. Okay. You could also call this your top speed or your V max, your maximum velocity. Okay. So this is your V max and not your saturation point. Okay. Can you give me, well, actually, we can go on from here. So when it comes to oxygen binding curves or enzyme activity curves, they're very similar to one another. And the important parameters on there are the same. Km gives us a sense of, well, how much does our enzyme want to bind our substrate? And Vmax gives us an idea of, well, how fast can this enzyme catalyze a reaction? Monitor with respect to our substrate's concentration. So our enzyme is typically going to be very slow whenever we don't give it a lot of substrate, and we're going to have a low initial velocity. At higher substrate concentrations, that's where our enzyme is going to kind of be the most active. Now, this is what an example of a enzyme catalyzed reaction plot looks like. This is also known as a Michaelis-Menten plot. Now, with that in mind, what we are interested in whenever it comes to evaluating enzymes is we want to know what is the Vmax. So what is the fastest that this enzyme can possibly go? That's one parameter we're interested in, Vmax. And a Michaelis-Menten plot tells us that. The other important parameter is our Km, because our Km tells us, well, how tightly does our enzyme bind to its substrate? Does it bind to it very easily, or does it take a lot to bind to it? Now, with that in mind, we always want to look at this and be able to kind of make a projection or a prediction as to what they are. Our Km is a x-axis value. So Km has units. Does anyone want to guess what those units are? And we could go back to this slide right here. Based on this slide right here, could you tell me what are the units for a Km? We've got two different units that we looked at here. Our Km is similar to our P50. Our P50 is measured in torr. Our Km is going to be measured in whatever units the substrate was measured in. So here, units for Km might be something like micromolar or nanomolar or heck, molar. Now, based on that, could you tell me what are the units for Vmax? Make an approximation as to what Vmax. Add it to the chat. Perfect. Millimolar per second. They're very similar to your units for velocity. Okay, so those are our parameters that we're interested in whenever it comes to studying an enzyme. Now, this plot right here, this plot represented by this blue line, follows this equation right here. This equation shows initial velocity is equal to our Vmax times our substrate concentration over our Km plus our substrate concentration. Now, this is what is known as the Michaelis-Menten equation. Now, I am going to spend about 10 minutes getting into the sugars presentation, which is titled Week 7, Day 1. Okay, so I'm going to switch my share. I'll do this for about 10 minutes, but then again, I'm sorry, I've got to cut class a little short to go pick up my kiddo. Sugars. Sugars are molecules that we are studying after enzymes because the thing that we're going to study after this is glycolysis. We're going to study a metabolic pathway. So sugars, if you think about these, you might be able to reference back to organic chemistry and think, okay, what were functional groups or what are the functional groups I see whenever I look at a sugar? I've got your list of learning objectives here when it comes to sugars, and I'm going to go through these as we proceed through this slide deck. First and foremost, sugar is more targeted and refers to a simple molecule, a monosaccharide and a disaccharide. Sugars can form polymers, and they can be hundreds of subunits or hundreds of individual units long. A saccharide is a more general term and includes simple molecules as well as polymers of them. So if you've ever heard the term polysaccharide, if you took a biology class and you learned about lipopolysaccharide, well, that's a lipid with a polymer of sugars on it. Carbohydrates is an even more general term that encompasses all of the above as well as derivatives. So carbohydrates, saccharides, and sugars are all terms that we're going to use in this section, and we'll kind of use a little bit of we'll use some of them interchangeably. Now, when it comes to monosaccharides, typically monosaccharides, we're talking about anywhere between 3 carbons and 6 carbons. Now, all of these will have the empirical formula of CH2O. Now, that's separated out here with CXH2OX because if we have 3 carbons, a 3-carbon monosaccharide will have the formula C3H6O3 because this will reduce down to that right there. Could you give me a 1 in the chat if you remember empirical formula and a 5 in the chat if you think, what? Empirical formula? Never heard of that before. Okay, so it's your lowest common ratio. Now, common sugars that I want you to know about, these right here. Glucose, fructose, ribose, galactose, and glyceraldehyde. Glyceraldehyde is your example of a 3-carbon sugar. Glucose, fructose, and galactose are your larger molecules. They have identical formulas, but there are some things that make them different. These are isomers of one another. Ribose is a 5 carbon molecule, a 5 carbon sugar. And whenever it comes to using these sugars with different numbers of carbons, we also introduce and implement the prefixes tri, tetra, penta, hex, hept, and oct. Now, I said we would typically use between 3 carbons and 6 carbons. A fair question for that of why is, well, most of the time sugars are going to cyclize. They're going to form ring structures. And what do we know about ring structures? Could anyone tell me what are the favored or more favorable sizes of ringed molecules? And I'm thinking the number 5 and 6, perfect. Smaller than that, a little bit less stable, a little bit less common. 7 and 8 or larger, even they're also less common. That's not to say they don't exist and they're biologically irrelevant, but that's like your 5 and 6 membered rings are so much more present and so much more abundant that they kind of almost ignore the other molecules. Now, when it comes to monosaccharides, it's important to know 3 carbons to 6 carbons is your common range. The next important thing to know about a monosaccharide is, well, what functional groups are present? Now, one of the things, or one of the terms that are commonly used is polyhydroxyl ketone or polyhydroxyl aldehyde. So there's lots of hydroxyl groups on a sugar, but when it comes to your biggest kind of like division of types of sugars, we have either our aldehydes, which this is represented, this is a 3 carbon aldehyde, and we also have our ketones, also known as ketoses. So this molecule right here is an aldose. It's an aldose because it has an aldehyde, and it is a sugar. Now, this is also known as a aldotriose because it is a 3 carbon aldose. Does anyone want to take a guess as to what this molecule is in terms of the terminology of aldose, ketose, tri, tet, pent, and so on? If you do, put it into the chat. We've got 1, 2, 3, 4. 4 carbons. This is an aldehyde. So we're looking at an aldotetrose. Give me a 1 if that makes sense. Okay, great. Now, in the next slide or the next figure that I show you, I want you to add an A for aldose or a K for ketose. Tell me what this one is. A for aldose or a K for ketose? Yeah, this is an aldose because we have our aldehyde functional group up there. Now, as an aldose, this is our 1st carbon, 2nd, 3rd, 4th, and 5th. So this is an aldopentose. Last but not least, an aldohexose. Now, before we proceed from here, another thing that I want you guys to work through with me is I want you to think about chirality. Whenever I think of chirality, I'm thinking about a carbon that is bound to 4 different things. And some of those different things could be a hydroxyl group, a hydrogen, a carbon chain, an alkyl chain, any number of things. So when I look at this carbon right here and all of my aldoses, this is carbon number 1. That carbon is bound to 3 different things. Double bound to an oxygen, a hydrogen, and a chain. So 3 different things. These carbons are therefore not chiral centers. Okay, so I'm going to circle those in red. Down at the bottom, this carbon right here. That's carbon number 3. Why is that number 3? Well, this carbon at the top gets my highest priority because this double bond to the oxygen is kind of like it being bound to 2 separate oxygens. So that's why this group has the highest priority. So this is carbon 1, 2, and 3. Now, carbons 1 and 3 are not chiral centers. Give me a 1 if you agree with that. Okay. Then, what about carbon number 2 here? Is that a chiral center, Y or N to the chat? It is. Okay. So I'm going to put a C here to indicate it's a chiral center. And then I'm going to go on to my next sugar. This is a chiral center. This is a chiral center. This is a chiral center. I'm going to put an X over my carbons that are not chiral centers. My terminal carbons are basically not chiral centers. So carbon number 2 in all of these is a chiral center. What about this one right here? Is that carbon a chiral center? Y or N to the chat? It is. Okay. So then that means this is. And then if I go over to my aldopentose, we've got 1, 2, 3 chiral centers. So then could you tell me in the chat how many chiral centers are present on an aldohexose? 4. Spot on. 4 is absolutely correct. Now, that is one of the things that I want you to recognize. I want you to recognize that as an important piece of information. Now, with that said, if you look at this aldohexose, could you tell me what is the carbon number of the highest numbered chiral center? What is the carbon number of the highest numbered chiral center? And for that, you got to go your priorities. So this is carbon 1, 2, 3, 4, 5, and 6. Okay, what is my highest numbered chiral carbon? Carbon number 5. Now, answer the same question, but about an aldopentose. What is my highest? Perfect. What about an aldotetrose? Great job. Okay, that's where I'm going to stop for today. I want you to be able to look at a sugar and identify the different numberings, identify the functional groups, identify the priority numbering, and the number of chiral centers, and being able to identify a chiral center. Now, with respect to chirality, it's not going to be a huge part of this discussion of sugars, but it's important to be able to see it and say, aha, that is bound to 4 different things, chiral center. Okay, could everyone give me a 9 in the chat if they feel good about this? And any other number or character if they're like, I don't know about this. Okay. Well, I'm going to say thank you guys very much for your time. I'm really sorry for cutting class short. I hope that you guys have a great weekend. If you have any questions, get back to me as soon as possible. And I'm in the process of wrapping up the grading for homework 1. And so if you got any questions about that, let me know. I will see you guys on Tuesday, and we'll take off from here. All right. See y'all.